Right, kia ora everybody. Yeah, I'm Phil Carlisle, Principal Network Architect at Chorus. I'm based in Ōtautahi, Christchurch. I've been at Chorus since it began actually, which was in December 2011 when we demerged from Telecom New Zealand. So Chorus is New Zealand's largest fibre wholesaler. Our network will reach over 90% of the population by the end of this year. All of the country's internet service providers are connected to the Chorus network. It provides a perfect way to tap into the geographical reach of New Zealand's largest fibre network to deliver services to more of the Kiwi population. In the process, it helps to create a more productive economy and enrich the lives of New Zealand consumers. Chorus operates a congestion-free network. In order to meet the growing demands for data, Chorus is continuously investing in this network. So in April, the average usage was about 560 gigabytes per month. That's a lot of Netflix movies. The average connection speed was around 345 megabits per second. So that's pretty good when you look around the world. Chorus assets include approximately 600 exchange buildings, 57,000 kilometres of fibre, 130,000 kilometres of copper, 60,000 kilometres of duct, 12,000 cabinets and 300,000 poles. We're a wholesale provider only, working in partnership with other organisations to provide services to end customers. Chorus does not just provide access to broadband. We offer high-capacity transport services such as backhaul and data centre interconnect. We also provide co-location services in our exchanges, as well as access to poles and other infrastructure. Now, in terms of precision time, I'm talking about precision time protocol based on the IEEE standard 1588. Precision time protocol is significantly more accurate than NTP or network time protocol, which is commonly used in the computer industry. It can deliver sub-microsecond accuracy, is implemented using hardware support, and what I'm talking about here is full timing support. So it's synchronous Ethernet, SYNC in combination with PTP, precision time protocol. So on that diagram up the top, just get the little laser pointer. So in typical implementation, you have a primary reference clock, which is like a frequency source. And then we have a primary reference time clock, which is also taking time of day. That goes into a grandmaster clock function. And then across a network, you have a number of network nodes. So in this example, there's 4. Every one of those network nodes has hardware clock equipment in it. So it's running synchronous Ethernet, which allows them to all have frequency lock. And then we also have boundary clocks for PTP. And then at the end of the chain there, you have a slave clock, which is like the client that needs an accurate time signal. So there's many industry uses for precision time. The biggest driver at the moment for us is mobile network synchronization, but it's also very important for power networks, broadcasting, finance, science, including the areas of measurement, astronomy, and space. So for synchronization, there's 3 types of synchronization. And I'll go through this because it should help understand why it's important for mobile networks. So there's this frequency synchronization here. So in that example, we have 2 clocks and they are aligned in terms of their repeating interval, although the pulses are not aligned. With phase synchronization, we've got the 2 clocks are aligned in terms of their repeating interval, as well as phase. So you see now all those pulses are nicely lined up. And then down here with time synchronization, we've got the 2 clocks are aligned up in terms of their repeating interval, phase, but they also are now sharing a common time reference. And so you'll see those patterns all line up as well. If I now go to the mobile example. So 4G and 5G mobile networks can use a technology called time division duplexing. And that's where the transmitting and receiving paths operate at the same frequency. And it's a bit like having a conversation that needs to be coordinated. So if you're talking to one person, talking to another person, if you talk at the same time, you're interfering with each other. So it is critical that multiple mobile sites transmit and receive at exactly the same time to avoid interfering with each other. And so that's where phase alignment is important. The sites must also transmit and receive in the same pattern and therefore must operate from a common time reference or time of day. So on these little diagrams at the side, it's showing sort of, you know, the transmission pattern for TDD signal, and the blue D, that stands for downlinks. That's when the mobile site is transmitting to handsets, and in the red you've got the uplink, which is where you've got handsets talking back to the mobile site. So if you get overlap there, like in that example, then that's interference. In the lower diagram, you can see everything's lined up nicely, and you have no interference. So for TDD operation, accurate timing and coordination across operators is important for maximizing the efficiency of spectrum use and to prevent interference between radio nodes. So GNSS, which stands for Global Navigation Satellite System, so that covers multiple systems that are used for navigation. GPS is one of those. So GNSS is commonly used as a source for precision time. Loss of precision time can have significant industry impacts. So there can also be issues with GNSS. Antennas must have a clear view of the sky. So an example there, if you go into a CBD where you've got very tall buildings and you want to install a little mobile site at street level, you're probably going to struggle to get a view of the satellites. So you then have to run cabling and install an antenna on the top of one of the surrounding tall buildings, and there's going to be a lot of expense involved in that. There's also significant costs with installation of GNSS receivers, and you can imagine if you're building a network with thousands of sites, that's potentially thousands of receivers you need. GNSS can be jammed or spoofed. So there's little pictures on the top right there. It's just some examples of jammers you can get. Get those on sites like AliExpress. The cigarette lighter example is quite useful for people who drive company cars but don't want the company to know what they're up to when they're in the car. Yeah, AliExpress. GNSS can have availability issues due to events such as solar storms or coronal mass ejections. Acts of politics or war can impact it. And then there's also been government directives. So it's like the US government has issued a directive a few years back requiring that there be a GNSS independent source of UTC made available for infrastructure owners and operators. With precision time protocol, it's possible to deliver precision time independently of GNSS. So in terms of distributing time on the Chorus network, Chorus operates a national DWDM network, which basically extends from Northland all the way down to Southland. DWDM stands for Dense Wavelength Division Multiplexing. That's where the the light that's shining down the fibre is divided up into many wavelengths. This technology overcomes issues of distance and limited fibre availability, so allows you to stack a lot of services into one pair of fibres. It can carry many services, or like I've said there. Each service uses a dedicated wavelength and typically has a capacity of between 100 to 400 gigabits per second, and that's constantly increasing as technology evolves. The DWDM network can be configured to have a dedicated optical timing channel, and this channel runs on a single fibre, which helps overcome asymmetry issues, resulting in a higher level of performance. So to equip the DWDM nodes to support timing, there's a couple of cards that we plug in. One is to set up the timing channel on a single fibre, and the other one has hardware clocks to support precision time protocol. So we've been running a technical proof of concept with quite a lot of help from MSL. So we've installed a small DWDM node and a enhanced primary reference time clock into the MSL time laboratory. And that primary reference time clock is connected to an MSL cesium clock. And you'll see on there that we do have a GPS antenna on it at the moment. So we do have some compatibility issues, which are resolvable, but during the course of this trial, we haven't been able to get time of day out of the MSL equipment. So we've been using GPS to do that for the purpose of the proof of concept. So from the MSL time laboratory, we've got about 40 kilometres of fibre, where we connect up to the Chorus laboratory, which is in Courtenay Place. In there, we have a network of 3 DWDM nodes, which have been fully equipped to support precision time, and they have various lengths of fibre connecting them together. We also have an optical line terminal. Optical line terminals are what we use all over the country to deliver UFB services. And the reason we have that there is so we can look at putting synchronisation or precision time over existing services, and then we can also deliver synchronisation as a service directly out of the DWDM node. So we've been borrowing some test equipment from various places, and we've got Stephen here who's been doing all sorts of testing. So some example test measurements that we have got there is on the short route, which is pretty much straight across through here, through these nodes, about 45 kilometres. We have a max absolute time error of about 30 nanoseconds that we measured, and then go in this longer route around here. We go through all of the nodes. It's about 95 kilometres. We have measured a max absolute time error of about 64 nanoseconds. So the proof of concept has given us confidence that precision time can be delivered nationwide using a network of fibre and DWDM. And we're currently working on a business case to hopefully get the go-ahead to start building that into our network. Gives us a traceability to a highly accurate, reliable clock source managed by a reputable scientific organisation. We expect to be able to achieve an accuracy of less than 1 microsecond nationwide. And that's expected to improve as technology advances. It also does depend on the design of how you build it out, what accuracy you can achieve. So that's about it from me at the moment. Thank you for your attention.